Thank you very much. It's great to be here at Quantum Korea. It's my first time visiting. I know this is, I think, the third year. Congratulations to the organizers, and I very much look forward to hearing all of the talks that are going to be taking place over the next few days. As was announced in the introduction, my name is Celia Merzbacher, and I'm Executive Director of the Quantum Economic Development Consortium. And I'm going to build on the presentation that Oscar Painter gave, where he explained some of the technology and the technology challenges. I'm going to focus on the practical applications of quantum technologies. And my title and the name of my organization, and in fact the name of the conference, does not have computer in it. So I will be talking about quantum technologies broadly, the application of the quantum mechanic principles and the ability to control matter at the scale that allows us to take advantage of quantum mechanical properties for all kinds of uses. So I want to sort of explain why you should believe what I'm going to tell you. This is not just me talking. I run an organization that has about 250 members in it. And it was started in 2018 by an act, a piece of legislation by the US Congress, where the Congress of the US directed NIST, the National Institutes of Standards and Technology, to establish a consortium of stakeholders. And they contracted SRI International, the company I work for, formerly Stanford Research Institute, some of you may know it, to create and manage the quantum consortium. So the consortium is really intended to bring together all of the stakeholders. That's a broad word, and it was on purpose, to include the organizations that will make technology commercial, but also recognize that there's a lot of research and learning that needs to happen also. When we were created, there was a big investment taking place in the US and by other nations to invest in the fundamental research and advance the science and knowledge. And at the same time, already, companies like AWS and IBM and Google and others were making big bets. So there was this practical development. At the same time, the science was happening. So there needed to be an organization to link these together. And that's what QEDC has become. So we have all of these purposes with the mission to enable and grow a robust quantum economy. We're really industry-driven. And to do that, we ask, what are the use cases? Where are the big markets? This is business, after all. And we also were tasked to identify gaps. Some of the gaps are in technology. And we heard about some of the challenges from Oscar Painter about error correction and the need to scale up the physical qubits, the logical qubits, and so on. But we also have gaps in measuring progress, metrics, benchmarks, standards eventually will be very important. There's a big gap in workforce, people with the right skills, and there are policy gaps. So we're here to identify these gaps and make recommendations for how to fill those gaps. We also do a lot of work to inform investors. Those can be public investors because the governments are making decisions where they should spend their money, where to focus. And then also private investors. VCs want to know where are the opportunities, how soon will we expect to see the ROI, and so on. And really, like any consortium or association, we are about connecting people who need to work together. Even a big organization like AWS or Google needs to partner with others to get the technology that they need to be able to build the systems. So this is a diagram that shows the makeup of QEDC today. It's about 70% corporate. That's the pink part of the diagram. Those companies include the big guys, but also primarily are small and mid-sized companies and startups. And we, a few years ago, opened membership to non-US companies, and about 1/3 of the companies are based outside the US, and 2/3 are based in the US. But all of those non-US companies want to do business in the US. They want to be connected to US customers and collaborators and developers. And so they often have operations and presence in the US, or they are planning to. And likewise, the US companies want to do business outside the US. So it's a very natural synergy that is taking place. So we have all these different sectors. We have some universities that are members, government laboratories, and others. And then we also have people from all parts of the stack, from the low-level, even materials companies, companies that make components that go into the systems, as well as the system developers, both hardware and software. And we even have end users and what I call service providers. For instance, a patent law firm is a member. So it's the whole ecosystem coming together to figure out what needs to be done to accelerate progress. We are, as I said, now open to companies and research institutes from many countries, the ones shown here in pink, including South Korea. And so it's a white list of countries we keep expanding, from which we accept applications. And whether the application comes from a US company or a non-US company, we do some review to make sure that they are in good standing and good members of the community before we admit them. So here's another map of the world. This one shows the most recent update from this organization, Curica, that tracks the government investment in quantum. And it's perhaps hard to read from the back of the room. You can find it online easily. But I just want to note that there are many countries that are investing public money in growing the quantum activities in their part of the world. The US, China, UK, Germany, and South Korea are the top 5 based on this data. So very impressive what's taking place here in Korea. A lot of growth. I had the chance yesterday to visit KIST, and they were talking about how much they were growing the work they're doing there, and that's happening all over here. So the total worldwide estimated, and this is cumulative over time, is more than $55 billion US. So, okay, we've got this big investment going on from national programs. What about the private sector? That's a little harder to estimate because I think companies like AWS don't like to talk about necessarily how much they're spending. But there are some publicly traded companies today, and there are some pure quantum companies. Of course, I like to say there are no large quantum companies. There are big companies that have a little quantum startup inside. So it's difficult sometimes to evaluate the economic activity at a big company. So QEDC did a report that came out in March. You can find it on our website very easily under publications, the 2025 State of the Global Quantum Industry. So this is something that a consortium that is sort of a trade association in a way would typically do. What's the economic impact of this industry, and how is it changing over time? So this is our first report. We will continually update it. What are the metrics of an economy? Well, there's things like revenue, workforce, patents, and so on, investments. And those are all reported in this simple, you can see it here, 5 pages report. So some of the numbers that I just am going to highlight a couple of the numbers. One is this sort of makeup of this industry. So we divide it into what we call partial play. That would include AWS and some other organizations, maybe a company that makes electronics, control electronics, like Keysight, for instance, has some quantum business. Some of their team is quantum-oriented, some is not. Then there are about 500 what we call pure play quantum companies. And for the pure play companies, you can see how they're distributed around the world. We intentionally kind of group them into regions. And in fact, North America and Europe has a slightly larger number of these pure play quantum companies right now. Another measure of economic impact is the number of workers. And this is, again, hard to get a firm number on, but we tracked both the number of jobs and also openings. And you can see here the openings and workers reported again by geographic region and There are now some, I forget the total number, it's in the report, but a significant number of workers. And I think this is a very important fact to communicate to the policymakers who often, they read the headlines, and we saw some of them in the last talk, quantum is going to be amazing, but it's still in the future. And in fact, there is a lot of activity. There are many jobs today. There is technology being made, and I'm hosting, or my organization is hosting a technology showcase on our Capitol Hill. We're bringing the technology to Congress, and we're going to let them see it in person. So I said, you can come and be an exhibitor at this showcase if your company is going to bring something that you can show to somebody. Make it real. And I think that's very important for all of us who are in this field to do, to talk to the public and policymakers about what's happening today as well as where it's going in the future. So we've done for 5 years now a survey to ask the quantum computing companies, what are your revenues now, and what do you expect your revenues to be in the next few years? And now that we've done this for several years, we see the trend in the data. It's quite consistent and steady, increasing about 27% year over year. And in fact, the bar for each year that's on the right is the actual number, and then you have previous year's estimates as you go to the left. And so, in fact, the actual number has always been higher than what was being predicted. So despite all the hype and sort of expectations that seem a little bit overinflated sometimes, the actual data is even more positive than some of the companies were saying it would be. So this is very encouraging, and we look forward to continuing to measure this progress in the quantum computing area. So some of the trends, and in this survey we ask questions in addition to what were your revenues and what do you expect them to be. And this is a survey that goes to companies worldwide now. We each year try to be very complete. We also ask questions, do you think that the access to quantum computing will be primarily via the cloud or on-prem enterprise systems? What algorithms do you expect to be where the revenue is made? What businesses and so on? So again, you can see the full report of the quantum computing market forecast on the QEDC website. But these are some of the findings. So every year, the access is expected to be mainly via the cloud. But access by on-prem is increasing, which is an interesting thing to see. So we'll see how that goes over time. The most promising end users tend to be research, chemicals and materials, and pharmaceutical, which is a type of chemical, I suppose. And then we ask a question that is a frequently asked question: when are we going to have a useful quantum computer? We define that as a utility scale. Utility scale will do something useful. It may not be the ultimate general purpose quantum computer. That may take longer. But half of the respondents said 2 to 5 years we'll have a quantum computer that can do something useful. But 1/3 say more than 5 years. So there's some difference of opinion. So this is the question that I think I get the most. I live in Washington, D.C. I meet with policymakers. They're smart people, but they don't know much about quantum, and they always ask this question: what's it going to be good for? So we'll just review. You heard a little bit from Dr. Painter, but I'll give you my answer to this question. Well, apparently it's going to be useful for all kinds of things. If you go on the internet, you can find lots of products that say quantum in the title. And some of them are sort of dangerous, like quantum ant killer that on the left, paint remover, that's going to be kind of harsh. It can clean your dishes. And then there are these categories of sort of health and wellness. There's supplements, quantum calm, that's very calming, quantum detox, it gets rid of bad things, I guess. And I like this one here on the bottom right. This is something you wear that's going to somehow improve your mood or something. And then my favorite really is the quantum vodka at the top there. Well, okay, so that just is sort of indicating the level of hype and the association between quantum and things that are state-of-the-art, better than before, for example. But in fact, quantum computers, and I'm focusing first on computers, then I'll get to sensors and networks, are generally kind of categorized in three areas. The idea that you could do some algorithms that could do a better job of optimization, the traveling salesman problem. This is sort of, I should make it a test. This is a diagram that's representing the electric grid. So the electric grid it's been around for a long time, right? But it was designed for big electric power plants, distributing the electricity out to the homes, very sort of simple arrangement. Now we have distributed solar and wind, we've got electric vehicles that plug in and out. All the sources and loads are much more complicated, and this grid has to be constantly in balance. It's really kind of amazing that it works, and there's a whole sort of market around that. So if we could do a better job of not only managing that balancing problem, but also predicting faults or detecting them. So, a bad day for the electric company is when your power goes out. They want to minimize that. So there are sensors and there are computing sort of technologies that may be able to help with that. So optimization kind of problems. We heard about the use of quantum computers for doing materials type modeling and simulation. I think there's widespread belief that that's likely to be one of the earlier use cases. This is the chlorophyll molecule, much more complicated than we can model today with basic principles. But chlorophyll, of course, is what plants use to convert sunlight to energy. If we could develop materials that could do that as efficiently as nature, that would be enormously impactful and useful. And then the idea that machine learning and AI could be benefited by quantum computers, interactions. QEDC actually put out a report recently on the sort of intersection of quantum computing and AI. There's quantum computing for AI. Could quantum computing help with coming up with data sets for training AI in ways that would be beneficial? There's a lot of interest in reducing the energy requirements of AI. Could quantum computing somehow decrease the energy demand for future AI systems? This is all somewhat in the future, but very interesting problems. Could AI help with design and development of algorithms, for instance, for quantum computing? So it could go both ways. So we did a study some years ago. Again, I'm very data-driven. I like to have some information to report. This was a study of all the reports we could find on using quantum computers for different types of problems, and indeed, they sort of fell into these main categories of optimization, simulation, and machine learning. And we put it into this nice diagram. This is at the top of the diagram. Then you kind of go down to the bottom of the diagram, and it looks a little bit more complicated, but this is showing where all of those different types of applications or types of problems apply in different sectors. So at the bottom we have the chemical and pharmaceutical industry, the airline and aerospace industry. We have life sciences, telecommunications, and so on. So there are many different sectors from a business point of view that will benefit from the ability to run these kinds of problems. So that's very exciting. There's big markets, and where do you sort of start is up to the people who are developing the software and the technology. Okay, so that's sort of the quantum computer part. Now I'm going to switch to a little bit about quantum sensors. And again, QEDC has done some use case studies. So we have many reports. You can find them on our website, and the title of the report is something like Use Cases of Quantum Technologies for X. And X, well, first of all, it may be quantum computers or quantum sensors, for example. Use cases for what? For biomedical imaging, for managing the electric grid, for logistics and transportation systems, and so on. So when you ask a quantum technology expert, what is a quantum sensor good at? They might say, well, it can measure all of these things. It could measure chemical distributions, electromagnetic, gravity, et cetera. You can see all of these things you can measure. But really, I think from a business point of view, the more interesting thing is who cares, who wants to do that kind of measurement? And so these are some of the applications of quantum sensors, depending on what you're measuring. You could measure if you can measure chemicals, you could measure biomarkers, for instance. You could measure environmental contamination, electromagnetic fields, you can measure brain imaging or heart cardio measurements, and so on. So there are many different kinds of sensors, and sensors are generally, in many cases, nearer term. In fact, some are available today, versus quantum computing, which is still developing, and the most useful computers are likely in the future somewhat. So there are a lot of work going on to develop them, and the question is, why would somebody use a quantum sensor? You know, in the business world, people don't care if it's quantum or if it's run by, you know, a windmill or something. They just want it to work. So what will it take for a quantum sensor to displace the sensors that we're using today? Well, it depends on requirements, for one thing. So this is a quantum clock at NIST. It takes up, you know, a big room. It's very, very accurate. But that's not very practical clock for most things. There was a program actually run by the DARPA Defense Agency to try to shrink this to something that would fit in your hand, called the chip-scale atomic clock. And in fact, it was a successful program, and you can buy this now commercially. It's, you can see, very much smaller than the size of your hand. Still not cheap, and cost is another factor always. You're not going to put something like this in every vehicle, for instance, if it costs many thousands of dollars per unit. So you've got to have the right size and power requirements and so on. But SWAP, I think many know you, size, weight, and power. So often those need to be smaller. Cost needs to be lower. Some fields have regulations. For instance, in medical use, there are regulations you have to follow, and so that can take additional time and money to achieve. And then there's a sort of question of standardization. Often, at some point, you need to have interoperability, and standards are necessary. And then there's sort of this adoption. How do you get the customers to actually switch from the old to the new? You have to demonstrate real benefit, and often it has to be substantially better than the existing technology, and in many cases, the existing technology keeps getting better without quantum. So this is sort of where we are today. Now, there is a technology that's being developed, it's very exciting, that replaces in some ways a big machine, this microencephalography machine that you use to measure your brain activity. It has to operate, it's using squids technology, so it has to be kept at very low temperature, so it has this big apparatus that sort of is from the top of the room. It's very sensitive to electronic noise, so it has to be done in a special shielded environment, a shielded room in a medical center, and the patient has to sit very still with this machine on. Well, that's not very practical for some studies. You want to have maybe the ability for a person to move and do activities while you're measuring. And then, of course, if you have children, they're not going to want to sit still, perhaps. So using quantum sensors, there are companies that are building these wearable devices that can make those same kinds of measurements. Now, they are still rather sensitive to the environment, so you still maybe have to do it in a special room. But it's a big advantage, and it's opening up certain possibilities. And these are in the clinical trial stage, so very exciting and moving forward quite quickly. So in our global industry study or report, we did also a survey to ask companies about their revenues and their expected revenues going out to 2028. And it's not as big a number as quantum computing. I didn't report, maybe if you couldn't see it, the quantum computing numbers today are around $1 billion US, and in a few years would reach $2 billion based on the expected growth. Here, the revenues last year in the quantum sensing space was reported about 375 million, but similar growth, 25% or so, going up to nearly 1 billion by 2028. This is based on responses from 67 different companies. The industries that seem to be most likely to take up this technology first are aerospace and life sciences. So I think that's something to sort of be aware of. And these are both industries that are willing to sometimes pay a premium for a better technology. So that's not surprising, perhaps. This was an interesting result. We asked these sensor companies how they saw the technologies evolving from concept, you could say low maturity at the top, to commercial. Between the light color bar is 2024, the darker color bar is 2028. And I think if you look at the two bars, the number of technologies that will be at the lab demo phase will go way down, and the number that's going to be at the commercial phase is going way up. So this is showing how quickly these technologies are moving from concept and prototyping to commercialization. It's very exciting. So I just have one slide to remind me to talk a little bit about quantum networks. So quantum networking is an area where there's a lot of excitement. The ability to perhaps have secure communications across increasingly long distances, for example. This is a chart that you can find online. It was done by the Center for Quantum Networks at the University of Arizona. That center is funded by government grants. And a few years ago, they asked some industry advisors, what are the applications for quantum networks? And that exercise led to 8 application areas that they chose. And you can see the top is quantum key distribution and secure communications. Then you have some that are very, I would say, science-based, long baseline interferometry, for instance. You have biological image and sensing, networking sensors. Down at the bottom, you have they broke separately clustered and distributed quantum computing, but somehow you have to network quantum computer modules. That may be because you want to take advantage of more than one type of qubit, or you're doing a hybrid system, or you're just scaling. Sometimes it's going to be necessary to scale multiple modules of QPUs, for instance. So these are all different examples of networks. So we use the word network quite broadly here. The thing that's interesting is the different axes on these spokes of these diagrams represent different requirements. And there's a code, a key, to tell you what those requirements are. How many qubits you need, what's the fidelity, what's the size, weight, and power requirements for this particular application, and so on. There are 8 different specifications, and they asked how dependent is this application on the performance along that specification. And these plots are very easy to look at and see that there's different requirements depending on the use cases of the network. And so the question, that's where they stopped. Now, I view these diagrams as each one is a target. It gives you something that says, if you can make a network with these requirements, that meets these requirements, then it would be useful for this application. My question when I see this is, how big is the market for each of those targets? Where is the target, or where is the diagram of where we are today? How close, how low are the performance characteristics today? And how hard is it to get from where we are today to where we want to be? Those are all very important questions from a business development, an economic and application question. So we're doing another round of this roadmap for quantum network applications, and we'll have an updated report hopefully by the end of the year. So what are the barriers to making progress in all of these different applications of quantum technologies? Well, number one is the hardware, and we heard about that from Oscar in his talk. This is a picture I took at a recent visit to, I think it was at University of California, Berkeley. This is not scalable. But a lot of, not just research labs, a lot of companies look like this when you go in and look at their systems. And so there's a lot of learning going on, there's advancements, there's new generations of systems that are being put together and tested and measuring progress that way. But it all needs to be more integrated, it needs to be more robust, and reliable for long-term operation. But we're kind of not there yet, so there needs to be more hardware. And as I note here, not just the number of qubits and the qubit part of the hardware, but the surrounding non-quantum technologies as well. We need lasers at certain wavelengths that are not available commercially. And those are sort of, when you go into a photonics research lab, there's just a whole slew of optics and lasers on a table to make the wavelengths that you need for these systems. Again, when you talk to the people who are doing research using lasers, they say, well, we've got all these different wavelengths depending on which atoms we're using and so on. So until we know which atoms we're going to use, we don't know which lasers we need to develop. So there's, again, another chicken and egg problem. We need to control electronics. There was mention of the need to be able to wire all the different qubits. That doesn't seem scalable. So there needs to be some clever advances in the control electronics and readout electronics and just integration in general. We heard a lot about error correction. So we need to improve the error and the noisiness of the qubits, but we also need to improve the error correction. And then we need algorithms. We don't have that many algorithms to run on quantum computers. Now, it's still early days. Now, there are quantum simulators out there. And so there's quite a lot of work going on to develop and explore algorithms. But in my opinion, we need more explorers today of algorithms. Because we need all three of these to improve in order to have a useful quantum computer, not just one. As I mentioned, we're going to need standards, and we need just to have benchmarks that we agree upon that reflect how you measure progress. Now, QEDC has been doing some work on benchmarking since 4 or 5 years ago. We report almost every year on our work in this area. We do what we call application-oriented benchmarking. So we're not measuring how many qubits, what's the qubit volume, not the sort of physical benchmarks. We're saying if you implement an algorithm in code and run it on a system, how well does that perform? How long does it take? What are the resource requirements and so on? And we're learning by doing this work that these systems are somewhat unstable. Sometimes it depends on what time of day you run the algorithm and so on. So this is all intended to sort of help the system developers improve their systems. So we need benchmarks, and ultimately we need some standards. And then we need people. And this is a problem all around the world. Sometimes I go to meetings and, among collaborators, and they say, well, we can all agree that we need workforce, so maybe we can collaborate on that. And I feel like that's actually the biggest competition is for the people. Everybody wants the people to come work for them. So how can we speed that up? Well, there's a lot of education going on. QEDC did a report early on based on a survey of the member companies where we asked them, what jobs are you going to be filling in the next few years? And for each job that they indicated, we asked for that job, what knowledge and skills do you want the person to have? And what degree would you like them to have from their education? And the interesting findings were that most of the jobs did not say quantum in the title. Most of the skills did not say quantum in the title. And most of the degrees that they wanted the people to have were not PhDs and not in physics. So we need to get the word out to the students that if you're getting a degree in a traditional engineering field, for instance, you can take a little bit of quantum education and be extremely qualified to enter a career in this field. In fact, I think that we're going to, over time, see the demand for engineers exceed the demand for physicists. Of course, in some companies, you need people with a PhD in some roles. But in many, there are people who need to have certain technical skills. We encourage students to get some hands-on experience. The companies say, we wish we could hire people with a little bit of hands-on experience using lasers or using cryogenic systems. So for the educators and for the students, or if you know somebody who's a student or an educator, please share that with them so that we can get the engine going and produce the qualified workforce. Meantime, I'm sort of promoting the idea that there are many people out in the existing engineering and STEM workforce who might be interested in moving into quantum careers. They need to perhaps go back and have a little bit of upskilling to get a little additional education and familiarity. And finally, I guess 2 points. One is when we look at the types of jobs that companies say they will be filling, there are the hardware developers, there are the software developers, and there are the business people. People in technical sales, people who are doing the business part of the company need to also have a little bit of understanding, but very different skills from the people who are doing the R&D. So there is sort of room for people with lots of different backgrounds, marketing and communications, very important, and so on. So the other point I want to make is that today we think of quantum jobs as being in the quantum development side of the ecosystem, what I call the quantum makers. But as this technology becomes useful and starts being taken up by different companies, pharmaceutical companies, finance, and so on, there are going to be more jobs in the quantum takers. The people who work in those industries need to have domain expertise and some quantum. So the skills that are required are going to continue to evolve over time. And I think it's very important to communicate that to the people who are in the pipeline today. So I'll just sort of run through a few conclusions and summarize what I shared with you today. I think we're all here because we're very excited about the promise of quantum technologies. I sometimes think I am preaching to the choir, as we say. You all are the ones who are as excited as I am, I think, for the most part, about what quantum holds for the future. It's going to have a very widespread economic value, and it's hard to estimate. There are some efforts out there by organizations like McKinsey and others who predict the value of quantum computing and quantum technologies that are really big numbers. And just like classical computing, I think it's difficult to imagine all the uses that will be made. I think that in the nearer term, when you have a new tool, a new computer capability, a new sensor, whatever, the first people who will go and use it are the scientists. They are extremely agile and quick to say, oh, wow, a new tool, and they go and use it. And they will experiment, and they'll play with it, and they will find things to do with it that hadn't really been imagined. And they will publish, and they will share, because that's what scientists do. So when these useful tools come along, I think there will be a blossoming of discovery that takes place. The market is growing, as I reported, and we will continue to monitor that, but it's still early stage. And while the revenue numbers look very positive, I will remind you that, in fact, very few of those companies are profitable. They're spending more money to make those revenues than they're earning. So that over time will change, but it is still early stage. And so it's important for the governments to continue to invest, to bridge to the future in a way that's going to be very important to keep the pace going. Challenges do remain, and you're going to probably hear about a lot of those over the next few days, but the investment is strong. The numbers for global investment, both in the public and the private side, continue to grow. And I think because of the amazing diversity of uses and the progress that's being made, that's likely to continue. So my sort of final takeaway is that the future of quantum is very bright. QEDC is excited to be part of the community that's accelerating progress towards that future. And I will be here for the next 2 days, so I would love to talk to you if you have any questions about the consortium. I look forward to meeting some of the representatives from the Korean quantum community at the expo and at the talks. And I hope you enjoy a Quantum Korea 2025. Thank you very much.